Thanks for taking the time to listen to our talk about Lake Ontario prayfish science and the roles of productivity and procedures. Instead of, if you've listened to these talks before, we often go through sort of a lot of time series and update the trajectory of different species. We want to do stuff a little bit different this year. My co-authors and I, we wanted to help explain sort of how we know what we know about prayfish and talk about how that shapes our conceptual model for what drives and changes prayfish populations. And then finally, we will finish up and talk a little bit about the alewife population and its trajectory. So we study prayfish for a variety of reasons, but they are a major part of the fish community. They often make up 90% or more of the biomass of actual fishes, and they're very responsive to biological or physical drivers and how they change. Similarly, they support decision making. They're great evidence for what non-native species do in the system, tracking native species restorations, and of course informing salmonid stocking numbers. This picture here is the alewife. It's a species of prayfish that supports a lot of popular sport fishes in the lakes, and decision makers understanding how many of those there are in the lake know how many fish to. We survey prayfish with these bottom trawl surveys, multiple agencies, state, federal, and provincial, all working together. And we do this across Lake Ontario. This demonstrates our survey from April of 2018. When we communicate these data, the results of these surveys, we like to talk about everything in a lake-wide estimate. So while we don't catch all prayfish in all places, we try to put everything on the same scale. Talk about a lake-wide estimate. We usually talk about a weight per area or biomass. So that's the total weight per area swept. And the area swept, we figure out with different sensors on the nets. And then we have that lake-wide average that's calculated in a stratified way. What's also important to know about the prayfish surveys is we trawl different times of the year, and we have historically, and we really understand how that influences how well we can catch certain species at different times of the year, because that changes. This is part of understanding why we understand what we do about different prayfish species. For instance, if you go out to survey slimy sculpin, and in the same year you trawl in both April and October, invariably, no matter what, you get more slimy sculpin, many more, in October than you would in April. Conversely, if you do that for alewife, you get the opposite pattern. You get far more alewife trawling in the April time period with the same trawls in the same year, so the biomass isn't changing that much. It's just the fish's availability to be caught by the trawl changes. So what that does on sort of a big picture scale is when you trawl changes sort of your view of the fish community. For instance, here are two images of what the fish community looks like in April, where every color is a different species, and that's sort of the proportion of that species in the community in April and October. Now, I didn't put species up there to tell you which community is which or which color is which species, but you just get the visual representation of how different those are. Here is the actual data to help you match those up, and you can see alewife are very important, especially in April, not nearly so in October. But when we combine these to sort of our best estimate in any given year, alewife definitely continue to dominate the community. And what's changed a lot recently in the community, proportionally, is which benthic species are most abundant. Round goby and blue have really proliferated since about 2004, and deepwater sculpin have come on since about 2010. That's a native species. We also are moving away from looking at individual means of a population, and we want to look at a whole population model. For alewife, that's really helped us identify our survey biases. For instance, here, the observations, the annual mean of our trawl surveys, like we talked about, are the points, but the population model is used It's basically 4 or 5 years before that and after to really get a good understanding of what that population estimate was at the time. And we see it's not always, sometimes it's running right through the points, but other times it's higher or lower. And that's a bias that we've realized has a lot to do with, we were previously only sampling in US water. Since we've moved to a whole lake sampling regime, we see less of that bias. But what we've seen more importantly is that's how the adult alewife had to look. And what we can then understand is what must age one fish had to have been to get those model results. And we compare those to our observations. And here we see a lot more drastic difference. The observations are well below the model. So in essence, the trawls are really likely underrepresenting age one, especially when abundant. And that sort of knowledge about our survey really helps when we're communicating to decision makers just how sure we are that there was not great reproduction or there was great reproduction in alewife. So while the community has basically stayed the same and been dominated by alewife, what's really changed is that biomass has declined by about 80% or more since the early 80s. And that's been strongly driven by alewife. And so it's that pattern that we want to try to understand more what's driving that. And there can be a lot of different things that determine how many and which prey fishes, right? It can be almost a dizzying number. Nutrients, different kinds of habitat, what species, how many predators there are. We think of all these as drivers. And in order to help managers understand and sort of bound the possibilities of what's available and how the lake can work, we have to kind of create a conceptual model that ranks these different drivers relative to each other as they influence the prey fish. The conceptual model that we use starts with the phosphorus concentration. That's phosphorus is a limiting nutrient in most lake food webs, and so it sets a bound or an envelope upon which fish biomass has to sort of stay between. But it can vary a lot based on how many piscivores there are. When there's more predators per the same unit of nutrients, you'll have less prey fish. Similarly, with more spawning habitat, you can have more. And then there's drivers that don't necessarily have a directional element to them. Weather and climate can be variable, as can invertebrates and non-native species. So well, first acknowledge this isn't something that we came up with. Really, this is an idea borrowed from folks working out in Wisconsin that showed just by changing whether you have predators or not in lake ecosystems, you can actually change the productivity of the system, but the nutrients ultimately sort of bound the possibilities. So what we find is that our observations do actually match our conceptual model well in Lake Ontario. Here I'm plotting the phosphorus in any given year relative to the prey fish, and phosphorus has declined over time very sort of concurrently with the prey fish. And we think it's just a productivity of the food web that's driving the prey fish biomass down. And it's not just prey fish. Here I've overlaid the warm water fish catch rates from the DEC Eastern Basin Warm Water Survey that spans the exact same time as the prey fish data. And here things like rock bass and smallmouth bass that we aren't catching in our prey fish survey, yellow perch, are all declining in a similar way as phosphorus has declined in Lake Ontario. So why it's important to think about phosphorus as an overall driver is because there's potential for things to become even lower concentration as concentration abatement is happening in Lake Erie. There's estimates that a 40% reduction in Western Lake Erie could result in about a 6% reduction in concentration in Lake Ontario, as well as a lot of other GLRI work up on the landscape to reduce nutrients. All great things, all really improve our water quality, but we have to recognize the concomitant trade-off that it does mean there'll be less fish in the in the lakes. Some other ways things have changed prey fish biomass that aren't just productivity is this observation where we get where the size at age has really increased for alewife. Different ages are in different colors. And look at that, like age 3. Sometime in 2010, an age 3 alewife was as heavy as an age 8 alewife used to be. And that's just it's kind of a big change in the system with how it works. And what we realized is that actually had a lot to do with when the Bythotrephes biomass, so that's the spiny water flea, when its abundance went up, all of a sudden alewife growth went up. So they're a larger food item. We think they help concentrate energy, make it easier for alewife to feed, and might actually extend the growing season for alewife, which as climate makes the growing season longer, there's some nice interplay there. So even though alewife biomass is declining because of nutrients, it might be increasing because of this invertebrate. Also, climate is getting warmer, right? We know that this data from our Monroe County water intake, um, it, it's increasing, what, about 32 years to go up a degree Celsius. I think that equates to about every 12 years for a degree Fahrenheit. But what's interesting of taking this idea of this driver and overlaying fish on it, these are the years where we have above alewife reproduction. You can see they tend to be the warmest years. These are the years in blue where we have below average alewife reproduction. So climate is playing a modifying role in there as well. And now, unfortunately, the current status of alewife is a little bit unknown because the 2020 survey was canceled the day after it began due to health concerns. We did initiate an emergency angler collected salmonid diet study, and we did that because in the past we've found the diets of the predators very closely match the diets we see, the size of alewife in the trawl. In fact, here I've just overlaid 5 different years when we have about 12 to 1800, 1200 to about 1800 diets in any one of these years, and we see the gray bars, that's the sizes of alewife in the predator diets, greatly overlaps with the sizes we catch in the trawl survey. Pay particular attention to these smaller alewife that are less than 150 millimeters. When they're present in the trawl, they're present in the diet. When they're absent in the trawl, they're usually absent in the diet. And that's important because in 2020, when we didn't have a trawl survey, we also didn't see very many of those fish in the diet, suggesting that there were few age 1 fish eaten in 2020 and therefore likely alewife reproduction in 2019 was probably low. So in thinking about the future for alewife, we're definitely predicting that our 2021 adult alewife will likely be at an all-time low. The combination of lower than average reproduction in years 2017, 2018, and 2019 will just naturally cause that adult biomass to be low. We know that phosphorus and productivity is bounding the system. So while we talk about, anglers will often ask, when do you think stocking can go back up? When will alewife go back up? Given the drivers we see right now, it doesn't look like it will be. Certainly climate can play a modifying role in there. If there's earlier, warmer springs, there's likely to be better reproduction. And then sort of the real wild card is how many predators are out there. That salmon's natural reproduction is a really important driver, but I've purposely stayed away from that because Mike Connerton's going to talk more about that. If you have any other questions, we hit on a lot of topics and went quickly. Please don't hesitate to reach out via email. And I would highly encourage you to check out the annual reports that are at these 2 websites here, both by the New York State DEC and Ontario Ministry of Natural Resources and Fisheries. Thank you.